We're going to consider another projectile motion problem in which we launch a cannonball or some other projectile at initial speed v0, but at an angle this time. So we're not going to launch it horizontally off of a table like in the last problem, but at some new angle, and I'll call that angle theta. There are a few questions that we can ask about such a projectile because it follows the same kind of motion, the only difference being the initial conditions here, the speed and the angle. We can ask how far will it go, so this is sometimes called the range. So if you're thinking about a football player punting the football, this is how far down the field the football will go. We can ask, as in B here, how long will it be in the air? Again, with our football analogy, this is the hang time. If the ball is kicked or punted, it spends a certain amount of time in the air before it lands on the ground again. We can also ask how high up in the air will go. That's this maximum height right here, where the ball has left the ground and goes up a certain distance. And lastly, we can ask at what angle will it strike the ground. So the angle of the ball is heading is constantly changing. The angle, of course, is related to the x component of its speed and the y component of its speed. Here, for example, the angle is 0. It's heading straight over to the side. Here, the angle is that angle theta. We can be asking what is that angle throughout the path of this ball. Before we get started on either or any of these questions, it's important to remember that the equations of motion for this ball are the same in the x and the y direction. In other words, x of t is just x naught plus v naught x t plus 1/2 ax t squared, and y of t is y naught plus v naught y t plus 1/2 ay t squared. And likewise, v in the x direction as a function of time is v naught x plus ax t, and vy, the y component of velocity, is v naught y plus ay times time. The only difference here is that the acceleration, which is a vector, is 0 minus g 0. In other words, its x component is 0. Its y component is minus g, and its z component is 0. So we can break our problem down. We don't need quite a three-dimensional system here. We can break it down to a two-dimensional problem. The y direction can be vertical, the height off the ground. The x direction can be the height, or the distance along the ground. And with these kinds of equations of motion, again, it's the same equation in both the x and the y direction. We're just going to have different constants to insert at various lengths away. It's the same equations of motion independently for the x and y component of velocity. It's just different constants we're going to insert for the initial speed and the acceleration. It's actually easiest to answer part B first. Why is that? Well, the ball is doing this. It's going up and then coming back down again. At this particular moment, right at the top of the arc, we will be able to sort of insert some knowledge here. That is that Vy, the vertical component of velocity, is 0. Remember that the speed is constantly changing in the y direction. This is Vx. This is Vy. Initially, Vy is positive, and Vx is up to the side like that. And Vy is shrinking as we go up the arc, and then eventually getting bigger and bigger and bigger as we go down the arc again, but in the opposite direction. At this particular moment, Vy is actually equal to 0. It's just like when we launch a ball straight up in the air, it goes like that. It's going up here, but the vertical component of velocity is getting smaller and smaller and smaller. It's 0, and then it's getting bigger and bigger and bigger, but in the opposite, in the negative direction. So we can insert that particular piece of knowledge here. that Vy at that time, whatever that time is equal to 0. So we'll say 0 equals V naught in the y direction plus a y t. And now we have a lot of unknowns here. We have to fill in for what V naught in the y direction is, the vertical initial component of velocity, and the acceleration in the y direction. Let's go back to our picture. The ball was launched at some speed, V naught, at an angle theta. So this initial vertical or y component of velocity is V naught times sine of theta. This is V naught. This is V naught y. This is V naught x, and that's theta. So V naught y is the vertical component of this vector. The acceleration in the y direction is minus g, and now I have a simple expression. V naught sine theta minus gt is 0, or the time that it spends going up is just that. Now that's not quite the answer to part B. That's the time spent to go up. In other words, to get to the top of the arc. It has to fall back down again, and actually that takes the same amount of time. So I need to actually multiply by 2. And that's the time that the ball will be in the air. So this is the answer for part B. We'll need to remember that a little bit further along. The other question we asked in part A was how far will it go? Well, the equation of motion in the x direction is x naught plus v naught x t plus 1/2 a sub x t squared. And we have to again fill in some constants here. We don't know how far it's going to go. That's what we're going to determine. But we're going to say that it started at the origin, so x naught is 0. This initial x component of speed, or velocity, will equal v naught cosine theta. And this time is the same time that we calculated from part A. So I'll just put that t from part A right there. And this last term is 0 because the acceleration in the x direction is 0. So this total x, which we'll call the range when the ball strikes the ground again, is when v naught cosine theta, I have to put in the time for the ball to reach the ground, where that time is. And there's an expression that the range equals v naught squared 2 times the cosine of that angle times the sine of that initial angle divided by g. Now I'm going to use a trig identity that the sine of 2 times an angle is 2 times the cosine of an angle times the sine of an angle. So that the range is v naught squared sine of 2 theta over g. It's worth just checking our units. This has units of meters, a velocity has units of meters per second, so this is meters squared per second squared. And acceleration has units of meters per second squared, so the per second squared down here cancels the per second squared up here in the numerator. And this has meters squared, but this has meters, so one of the meters squared in the numerator gets canceled away. So this is actually checks out in terms of units. And here's our answer to part B. So this says something perhaps intuitive, that the ball will go further the faster I kick it, but it also depends in an important way on this angle theta. This sine of an angle is always less than 1 or less than or equal to 1, but it equals 1 when the argument of the sine function is 90 degrees, or in other words, this theta is 45 degrees. And so football players know that if you're going to punt, you don't punt straight up and you don't punt straight forward, you put an angle of 45 degrees or something pretty close to that if you want the ball to go as far as you can. The next question was, how high will it go? We're going to go back to our expression for the position as a function of time. And there it is. We're going to again fill in. We don't know how high it's going to go, but at that time, we're going to insert everything we can here, including the time, and find out what that maximum y is. The initial y is 0 because we're starting out at the ground. This initial speed in the y direction is v naught sine theta. And the time that we're going to insert here is the time that we calculated at the very beginning. In other words, the time by which the speed in the y direction goes to 0. That time turned out to be v naught sine theta over g. Notice there's no factor of 2 now. And then we're going to have this last term in this expression plus 1/2 minus g we're going to put that same time in v naught sine theta over g, but now square it. So this equals v naught squared sine squared theta over g minus 1/2 v naught squared sine squared theta. That's from squaring these two things. Now it should be divided by g squared, but it's going to be canceled by one of those g's. One of those g's will be canceled by the g up front. So I have that. And notice this thing is the same as that. I have a half, so I have something minus a half of something, which gives me this. And that's our answer for part C. There's something somewhat intuitive here. This is the height, the maximum height the ball is going to go in the y direction. Football players don't necessarily want the ball to go the highest, but if they did, they can get it to go higher by kicking it at higher speed, or by kicking it at an angle such that the sine goes to 1. When does that occur? At 90 degrees. In other words, they kick the ball straight up like this. If they kick it off at some angle, its trajectory looks like that. It won't go as high, even though they kick it at the same speed. The last question we asked was at what angle will the ball strike the ground? Well, remember that the ball strikes the ground at some time 2 times v naught times sine of theta divided by g. So we're going to use that in our expressions. Now, the ball is coming down, and it's going to strike the ground here. It has some x component of velocity, and it has some y component of velocity. So the angle theta we can always find from the tangent of Vy over Vx, because this is the final velocity vector, and that's always the case that this is theta. So let's calculate Vy and Vx at that later time. Vy is equal to V naught y plus AYT. And in this case, V naught y is V naught sine theta, and AYT, well, the AY is minus G, and that time is 2V naught sine theta over G. Notice that this G and that G cancel one another. And I find that Vy is V naught sine theta minus 2 V naught sine theta, which is just minus V naught sine theta. Actually, that's interesting because it means that the ball was initially heading up at some speed Vy. Here's V naught, and I have a Vy component. Now it's heading down the same, at opposite Vy. Vx at the end of its trajectory is V naught x plus ax times time, while V naught in the x direction was V naught cosine theta. And there's no acceleration in the x direction, so the second term is 0. And this just says that Vx when the ball lands is V naught cosine theta. It's the same as it was, in other words, at the very beginning of the ball's path, which is fine because it's just moving at constant speed in the x direction. This says that tangent theta at the end, the final tangent theta, if I take that ratio, this is minus V naught sine theta over V naught cosine theta, just inserting for what Vy at the end is and V naught in the x, or Vx in the x at the end will be. Notice that the V naughts cancel, and this is minus tangent of theta. So when does this final angle have a tangent that's minus the initial angle? It happens when theta final is equal to minus the initial angle. In other words, the ball is heading down at the same angle as it was heading up.